Chinese remainder theorem. It is a theorem which discusses the possibility of solution to a system of congruences under certain conditions. It states that if we are given a system of congruences of the form x congruent to a1 modulo m1, x congruent to a2 modulo m2, and so on, x congruent to ar modulo mr, where each pair of moduli is relatively prime, then the theorem claims that there exists a simultaneous solution small x to all of these congruences, and any two solutions to this system will be congruent to one another modulo capital M, where capital M is the product of all these moduli. First, we prove the uniqueness of solutions. We assume that x and x dash are two solutions, then x satisfies the given system, so x will be congruent to a1 modulo m1, x congruent to a2 modulo m2, and so on, x congruent to ar modulo mr. Similarly, since we assume that x dash is also a solution to the given system, x dash also satisfies these congruence relations. Now, if we consider the first relations, x congruent to a1 modulo m1 and x dash congruent to a1 modulo m1, we get x congruent to x dash modulo m1. Since congruence relation is transitive, we have x related to a1 and a1 related to x dash must imply that x related to x dash. Similarly, we get the congruence x congruent to x dash modulo m2 and so on, x congruent to x dash modulo mr. Thus, we have a set of congruences x congruent to x dash modulo m1, x is congruent to x dash modulo m2, and so on, x congruent to x dash modulo mr. We can combine all these congruences to get the new relation x congruent to x dash modulo capital M, where capital M is the product of all these moduli. Here, to combine these congruences, we have used the result which states that if a congruent to b modulo m and a congruent to b modulo n, where m and n are relatively prime, then a should be congruent to b modulo their product mn. This is the result we used to combine these congruences to get our relation x congruent to x dash modulo capital M. Thus, we have obtained that any two solutions, say x and x dash, to the given system will be congruent to one another modulo capital M. Thus, the proof of uniqueness is complete. Now, to prove the existence of a solution to the given system, we construct a solution. For that, we first construct these numbers, say capital Mi, which is defined as capital M divided by small mi, where capital M is the product of all the moduli. By this definition, capital Mi will be equal to the product of all these moduli except small mi. Then, the GCD of small mi and capital Mi will be equal to 1, since small mi and m1 are relatively prime. Similarly, small mi and m2, these two numbers are also relatively prime to one another, and so on. Mi is relatively prime to each factor in this product, so that small mi will be relatively prime to capital Mi. That is, the GCD of small mi and capital Mi will be equal to 1. So, we can find two integers, say ni and n dash I, such that the linear combination of small mi and capital Mi will be equal to the GCD 1. Here capital Ni and capital N dash I are the coefficients of these two numbers, small mi and capital Mi. The existence of these two integers is already proved using Euclidean algorithm. From this relation, we get the result that mi into ni minus 1 is a multiple of small mi, which implies that mi into ni is congruent to 1 modulo small mi. Thus, we have proved the existence of an integer, say capital Ni, such that mi into ni, capital Mi into capital Ni is congruent to 1 modulo small mi. That is, capital Ni is the multiplicative inverse of capital Mi modulo small mi. Then we can observe that small ai into capital Mi into Ni is congruent to ai modulo Mi by multiplying both sides of this congruence by ai. We get this relation. And for j not equal to I, if we consider the product aj into capital Mj into Nj, then we already know that capital Mj, this number, is divisible by small mi from the definition of Mj itself. That is, aj into capital Mj into Nj will be congruent to 0 modulo mi. Thus, if we set small x equal to summation over I ai mi ni, that is the sum of all such terms, then x will be congruent to ai modulo small mi. Combining these two congruence relations, we get x congruent to ai modulo mi. That means x satisfies every congruence relation in the given system of congruences. That is, this x is a solution to the given system of congruences. Hence, we have proved the existence of a solution to the given system as required.